Now that we have completed our discussion on the Fourier analysis of the direct lattice and the reciprocal lattice, we are ready to see why reciprocal space is physically important. In this section, we will discuss how waves interact with crystals. The key idea is that a crystal is a periodic structure, and whenever waves encounter a periodic structure, they can undergo diffraction. This diffraction phenomenon is what allows us to experimentally determine crystal structures. Historically, the most important example is X-ray diffraction, but the same principles also apply to electron diffraction, neutron diffraction, and even optical diffraction from periodic structures. So here we will focus on two central concepts. First, the diffraction of waves by a crystal lattice. And second, the concept of Bravais zones, which will become essential later when we discuss electron band structures. So before discussing Bravais zones, however, we first need to understand the diffraction conditions for waves interacting with a periodic lattice. Before we discuss the diffraction of waves by a crystal and the so-called Bravais zone from which the semiconductor band structure is calculated, let's talk about a fundamental question as to why study the Fourier transform of a Bravais lattice. To answer this question, we need to understand how the crystal structure is studied. X-ray was first discovered in 1896, and X-ray diffraction of crystals was discovered and described by Max von Laue in 1912. It is the most commonly used technique to study crystals up to the present day. And we know that while visible light has a wavelength ranging from about 400 to 760 nanometers, X-rays have wavelengths from about 40 to 400 picometers. So the wavelength of an X-ray is much shorter than that of visible light. The figure shown on the left is the schematic diagram of the X-ray diffraction technique. The X-ray is first generated from the X-ray tube by accelerating electrons up to some voltage and smash them into the metal to generate X-rays. Then the X-ray beam is formed by passing the X-rays via a pinhole on a LED screen. The X-ray beam then hits the crystalline structure shown here. Each lattice plane or atom in this solid is kind of like a slit in a double slit experiment. On a screen far from the crystalline structure, you'll get a very interesting array of spots of constructive interference of scattered X-rays. This sometimes is called X-ray diffraction, although it's not really the accurate term. So when we say far from the crystal, the question is how far is far enough? Generally speaking, if the distance from the crystal to the screen, here denoted by the small case r, is much larger than pi d squared divided by lambda naught, where d is the largest dimension of the crystal and lambda naught is the free space wavelength of the X-ray, then we say the screen is in from Hoover regime, and the diffraction observed in this regime is called the from Hoover diffraction. Later in this section, we'll derive the equation of the far field scattered wave from the local charge density n of r. So the equation will be something like this, where n of r, or n of r prime, denotes the charge density, or electron density if you want, which is a periodic function following the same periodicity of the crystal. And here just a heads up, by observing the integral shown here, We see that the far-field scattered wave is in the form of the Fourier transform of a periodic function, which is, as we already mentioned, n of r, the charge density or electron density if you want. And in this equation, k and k prime denote the incoming and outgoing wave vectors, and we'll see that the difference between the two vectors must be equal to a reciprocal lattice vector G for constructive interference of scattered waves. Okay, so if the equation here looks not familiar to you, that's fine. Don't worry, and we'll give you a pretty thorough derivation later in this section. Therefore, spots in the diffraction pattern of a crystal, as shown here, correspond to lattice points in the reciprocal space, as the Fraunhofer diffraction is the Fourier transform itself.